good morning, and welcome to your last pre-recorded maths lesson. We can't wait to see you back at school on Wednesday, and we hope to keep up the momentum that we developed with online schooling. But it's going to be so good to see you again. Righty, let's get into this incredibly long word or concept called simultaneous equations. Now, you're going to be so happy to know that you've already been doing these when we've covered functions. So this is a little bit of an afterthought, but it will help you going forward when you are asked to solve equations and you don't necessarily see the picture in front of you. However, we'll get into that in a jiffy. For now, I just want you to consider two straight lines on the Cartesian plane. Let's call the one straight line y equals a half x plus 1. You can see its gradient is pretty, it isn't too steep, so that's why the green line's gradient could be a fraction. Its y-intercept is above the x-axis, so it's a positive number. So y equals a half x plus 1 does make sense for this equation, for this green graph. What about the yellow one? Y equals negative x plus 4. Yes, the y-intercept is higher than the other y-intercept plus 4. Negative x means the gradient is on a decline. If you were walking left to right, you would be going downhill. This is a decreasing function. So yes, this equation suits the yellow line. Now, what is that beautiful little point at which they cross over? That is called the point of intersection. Now, simultaneous equations is merely solving for a point of intersection. And we know at a point of intersection, there's an x coordinate and a y coordinate. Note how the coordinate has two parts, and an x part and a y part, and we have two equations. So the amount of unknowns at this point, the x is unknown at this stage, and the y part of the coordinate is unknown at this stage. The amount of unknowns must be the same or less than the number of equations given to us. And we have been given two straight lines. They each have an equation, and so we can solve for these two unknowns, x and y, right there. Now, at the point of intersection, the two graphs are equal. So I've taken the right-hand side of each equation, y equals negative x plus 4. I've represented it here on the right-hand side of this equation. And for the green graph that says y equals a half x plus 1, I've represented a half x plus 1 on the left-hand side of the equation. Essentially, I'm saying y is equal to y. Our two y values are the same, so our two equations at this point will be the same. Now we fortunately have a linear equation with only one variable, being x, and so we can solve for x. When you see one fraction, you can convert them all into fractions, and it's very clear that the LCD is 2. So every single denominator that is not a 2, I'm going to multiply by 2, and I'm going to be cheeky and skip a step and not write my denominators in the next line. All I've done here was 1x already had a denominator of 2, so it stayed 1x in this line. 1 over 1, we needed to multiply this denominator by 2. What you do at the bottom, you do at the top. That's why this 1 turned into a 2. Minus x over 1, we needed to multiply this denominator by 2. So what I do at the bottom, I do at the top. So I got negative x times 2, gives us negative 2x. 4 over 1, we need to multiply this denominator by 2. What you do at the bottom, you do at the top. 4 times 2 gave me 8. Now we get all our variables to one side. I'm taking that negative 2x over to the left-hand side. You'll end up with x plus 2x. And I'll take this positive 2 over to the right-hand side and get 8 minus 2, which will leave me with 3x equals 6. Divide both sides by 3, and we get x equals 2. Now, what on earth does that mean? That means that the x part of the coordinate of the point of intersection is a 2. Beautiful. We've done 90% of the work, but we're actually only halfway there. We still need to solve for y. Now, if only we had an equation that would tell us what y was if we had an x value. Yes, we do. Yay! We have two equations that we could use. I'm just using this one up top here because I'm avoiding fractions, but if you used y equals a half x plus 1, you'd be perfectly fine as well. So now I know x equals 2, so I'm going to go and replace my x with the value 2. So when x equals 2, y equals negative x plus 4. And instead of writing x, I'm writing 2. Y equals negative 2 plus 4, which gives you 2. So that means that the coordinate of the point of intersection is a 2 and a 2. What have we just done? We have solved a simultaneous equation. The only way this differs from what you are used to is that sometimes we can give you these two equations without the graph, and you can actually find the point of intersection between these two graphs without seeing a picture of it. All you need to remember is that if there are two unknowns, you are going to have at least two equations to work with. So in this case, there was an x and a y as your unknowns or your variables, and we had two equations to work with. So let's see. I'm going to change these exact two equations. I'm just going to manipulate them a little bit to see how we can solve simultaneous equations when we don't have a graph to refer to. So simultaneous equations, like I said before, are merely finding the points of solving simultaneous equations is merely finding the points of intersection between two graphs. I put the S in bracket because what if the two graphs are not straight lines? Or it could be a parabola and a straight line. And you know if a straight line cuts through a parabola, it will cut through at two different points. Or you could have a hyperbola and a straight line. You could even have a hyperbola and a parabola. And sometimes there could be several points of intersection. Now, there are very, very various ways in which you can solve simultaneous equations, but we will never expect you to stick to a certain method. You choose what works for you. My favorite method is the one I've just covered, whereby I imagine the graphs I imagine the equations as their functions, and then I think, okay, I'm solving for their points of intersection. If your knowledge of functions is good, simultaneous equations will be super easy to solve. In any case, I'm going to run through two little methods. One is called substitution. So now we're asked to solve the following equations simultaneously. Now, substitution is what it is. It tells you it's in its name. Firstly, let's double check that the number of equations matches the number of unknowns or variables. Yes, I see an x and a y, two unknowns, and two equations. You can actually title your equations or label them a certain value or letter or anything just to make it simple for you. So I'm calling this equation at the top equation number 1, and this equation at the bottom can be called equation number 2. Now the step to that substitution, step number 1, requires you to isolate one variable. What do I mean by isolate? I mean change the subject of the formula so that in one of the equations, one of the variables is all by itself. This is a lovely example because I didn't have to do any work. Y equals negative x plus 4 already has y isolated on the left-hand side of the equal sign. Y is already the subject of the formula for this equation. So in equation number 2, I've already got y isolated. Now let's see where else do we see another y in equation number 1. Because once the variable is isolated, we can take whatever it is equal to. See how I've put it in italics? Whatever this variable is equal to. Y is equal to negative x plus 4. That's another name for y. It's its secret identity. It's another outfit. It's another appearance. I'm not too sure what to call it, but y has a secret identity, and that is negative x plus 4. We can substitute this new outfit identity into any other place where we see a y. Now in equation 1, do you see we have a y right there? We can take that y, minus x equals 2 minus 2y, but instead of placing a y here, let's place what y is equal to. And from equation number 2, you can see y is equal to negative x plus 4. Voila! Back to grade 8. We now have an equation with one variable only that we can solve. On the left-hand side, I've just jotted down that I have substituted equation number 2 into equation number 1. You never have to write that down, but if you do like to jot down what you're actually doing just to have a sense of organization or clarity for yourself, you are welcome to. Here we go about solving for x, and eventually we'll see that x equals -2. But remember, we're solving for a point of intersection actually. See how this first line, because there's no x squared or there's no fractions, it means that this is a straight line and this line is also a straight line. I've actually used the equations from the first slide of the slideshow. I've used the exact equations. I've just manipulated the way they look by multiplying. Anyway, we now know that x equals 2, so now we need to find a corresponding y value. Luckily, we already have y all by itself in equation number 2, so I'm going to substitute x equals 2 into the second equation. Y equals negative x plus 4, but instead of writing negative x, I can write negative 2 plus 4, and that will give us y equals 2. We have solved these equations simultaneously. Here's another method that you really don't have to use. If you want to stick to the very first approach at the beginning of this video, whereby you isolate y for both equations and then you equate the equations and solve for x, that is perfectly fine, but elimination is a very cute technique to use when you see something special. Once again, I've used the same example, the same 2 straight lines, believe it or not. If you were to sketch these straight lines, you'd get the same picture as what we'd had in the first slide. But I'm just changing the way it looks. Elimination is a great technique to use when you see a variable's coefficient matching up with each other. In other words, this equation number 1 has a 1x, and this equation number 2 has a negative 1x. So those coefficients are so similar to each other, they can perhaps cancel each other out. So say I call the top equation number 1, the bottom equation number 2. If you were to line up the variables with each other, in other words, write the equations such that the x's are on top of each other, the y's are on top of each other, and the constants are on top of each other, then you can add these equations together. If I were to take this equation number 1 and add it to equation number 2 and only add my like terms, do you see on the left-hand side of the equal sign, we'll have 2y plus y gives us 3y. Then the positive x plus negative x cancels out. They are eliminated. We have eliminated a variable. We've got rid of this x. And our 2 plus 4 gives us the 6. So this 6 over here is going to help us solve for 3 times y. Divide by 3 on both sides and we get y equals 2. Now, this method got rid of the x, so don't forget, you still need to take this value of y and substitute it back into one of these equations. I'm going to sub it back into equation number 2, and then you can solve for x. So I'm substituting y equals 2 into equation 2. So instead of writing down y, I'm writing down what y is equal to, which is the number 2. 2 equals negative x plus 4. Solve for x, and you get x equals 2. So once again, we've found that the point of intersection of these 2 straight lines is 2 and 2, but we've done it in a different manner. Now, if these equations, another method for elimination can be done by subtracting one equation from another. Do that when one of the variables' coefficient in each equation is the same number and the same sign. So for example, what if it was 2y equals x plus 2 and y equals x plus 4? Same variable, same sign of the coefficient, and same number of the coefficients. Then you can use elimination again. Quick example before we leave you to do your homework. Here we asked to solve the following equation simultaneously. Note that sometimes you can be asked to solve the following system of equations. So if you see the word system, then you know it also relates to solving equations simultaneously, basically finding the points of intersection between two graphs. Here I hope you can recognize that the top graph, y equals minus x plus 1, is merely a straight line, and 2 over x equals negative y. Let's just flip that round to have y equals negative 2 over x, and then I hope you realize that that is a hyperbola. In quadrant 2 and 4, that hasn't been shifted up or down at all. So check out how the horizontal and the vertical asymptotes are just the y and the x axes. Then let's see, minus x plus 1 would look something like that. And what do you know? There are not only one, but 2 points of intersection between these graphs. You don't need to know this in order to solve your equations, but it is so advantageous, or it will stand you in such a good stead if you do have the ability to link equations to what they would actually look like on the Cartesian plane. Righty, so let's label our equations. The yellow one in the straight line, I'm going to call equation number 1. The green hyperbola, I'm going to call equation number 2. And luckily, y is already the subject of the formula for each. Y has been isolated for each. So I can equate what y is equal to in each equation to each other. Therefore, I'm taking the right-hand side of the yellow equation number 1 and equating it to the right-hand side of the green equation number 2. Here we've got a fraction situation going on, and you've been practicing this for the past week already, so we can work with solving for x if we see some fractions. We just make the LCD x, and so I've been cheeky and I've just multiplied every single term by the LCD just to save some time, and I hope you realize we've got a trinomial right in front of us. How do we solve a trinomial when the variable in the front is a negative? We can just take each term in the trinomial on the left-hand side and the right-hand side and divide it by -1, which I've shown in that rectangle. However, you don't need to show that working out when you do it. Right, the reason we divide by -1 is because we know the right-hand side of the equal sign will still stay 0, but it will help us change the sign in front of each term on the left-hand side of the equal sign. Look at how negative x squared has become positive x squared. Positive 1x has become negative x. Positive 2 has become negative 2. And now we can factorize that into 2 brackets and realize that x is either 2 or x equals -1. Why do we have 2 answers? Because there are 2 points of intersection. Look at how positive 2 links up to the orange point of intersection on the right-hand side of the y-axis. And look at how the blue, x equals -1, would be the x value of the coordinates of the points of intersection on the left-hand side of the axis. So great. We've got halfway there, 90% of the work, but only halfway there because we still need to find the y values of the points of intersection. So now let's look at this orange point over here. We know x equals 2. So when x equals 2, y equals -2 plus 1. Where the heck am I getting that? I'm just substituting it back into equation 1. You could have also substituted x's value back into equation 2. Whichever works for you, you go for it. It doesn't matter. You will get the same answer. Okay, so y equals minus x. X is 2 plus 1. So -2 plus 1 gives us the -1. And then we repeat that for the blue, x equals -1. We substitute that into y equals -x plus 1. Negatives will cancel, and you get y equals 2. And so now we have solved for the 2 coordinates of the points of intersection. If you didn't know that, that's okay. Follow the steps given under the method of substitution, and you will get the exact same answer. Good luck for your homework, and please reach out if you need any help.